In today's lesson, we're going to be looking at interference and diffraction, things that happen because light is a wave. Interference happens when you have two bits of light that can add constructively or destructively. This light is typically followed two different paths, and when you bring the light back together, you'll have two different light waves. If the light waves are matching each other, if they have the same phase, then the peaks will match up with the peaks, the troughs with the troughs, and when you add them together, you get an increase in amplitude for the light wave. On the other hand, if you have a shift between the two light waves, so you have a phase shift, and if that phase shift is half of a wavelength, then the peaks will match up with the troughs, and when you add these two light waves together, they will destructively interfere, and if they had the same amplitude, they would cancel each other out completely. To observe interference, you need certain conditions to make the observation easy. For one thing, you need two coherent sources of light. You need light coming from two different places that maintain the same phase offset. So one way of doing this is to have one source of light and then split it into two paths. You'll see in lab, you'll be looking at interference phenomena where you use a laser, and then sometimes you can send that laser down different paths, and that will result in some interference. You also need to have identical wavelengths. So interference can most easily be observed when you have a single wavelength of light. Here you could see someone who is creating an interference pattern with water waves instead of light waves. They're bouncing a couple of balls up and down in the water, and the balls have coherent motion with each other. They're going up and down at the same time, and you can see that there are places where the water waves are adding together constructively, and there's a high amplitude water wave, and then there are other places where the two water waves are completely canceling each other out, and the water is not moving up and down. One device that makes use of interference from light is the Michelson interferometer. The Michelson interferometer is used to measure very small changes in distance. So this interferometer consists of a laser which shines on something called a beam splitter. So this is a mirror whose surface is half silvered, so half of the light actually goes through the mirror and the other half is reflected. Then these two beams of light go to end mirrors where they are reflected back to the beam splitter and recombine. Finally, the light goes to some output port where it is observed. Now, usually the setup of this is such that the two waves of light coming out the output are destructively interfering. So they are set up so that the peaks match the troughs and they cancel each other out and no light comes out the output port. However, if the mirrors move so that the two arms are no longer equal length, so maybe one mirror is moved towards the beam splitter, the other away, although you could have just one mirror moving, and in that case this mismatch between the waves is no longer there. They might match completely or at least partially, and so light will be coming out of the output port. One of the largest examples of Michelson interferometers are the LIGO observatories. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory. These mammoth interferometers were built to measure gravitational waves coming from things like supernova explosions and black hole collisions happening way out in the universe. So these very exciting events create something called a gravitational wave. It's a ripple in the fabric of space itself. And when a gravitational wave passes through, it does what you see Einstein doing here. So it can stretch and squeeze space-time. It will stretch it in one direction, compress it in the perpendicular direction, and then oscillate back and forth. Now you don't notice this happening on a daily basis because these gravitational waves are incredibly weak by the time they reach Earth. They're very, very small, and in fact, if Einstein here were the size of the planet Earth, his stretching and squeezing would be less than the diameter of a proton. So these changes are incredibly small, but they can be measured with the enormous Michelson interferometers that make up the LIGO observatories. In fact, the distances between the beam splitter, so the laser and the beam splitter are in this main building, and the end mirrors are in these buildings far, far away, 4 kilometers away from the main building. So these observatories, along with another observatory in Italy called Virgo, have successfully measured gravitational waves coming from black hole collisions and neutron star collisions, and have found out new things about these objects.